Imagine a world where everything is the opposite of what we know. Instead of positively charged protons, atoms have negatively charged antiprotons. In place of negatively charged electrons, we find positively charged positrons. This isn't science fiction, it's the realm of antimatter. Antimatter is a fascinating concept in particle physics. It's like the evil twin of ordinary matter, identical in every way except for its opposite charge. For every particle of matter, there exists an antiparticle with the same mass but opposite charge. The existence of antimatter was first predicted by physicist Paul Dirac in 1928. His equations, combining quantum mechanics and special relativity, suggested the existence of these mirror particles. The discovery of the positron in 1932, the antiparticle of the electron, provided the first experimental confirmation of Dirac's theory, and opened up a whole new world of particle physics. Let's delve into the specifics of these matter-antimatter counterparts. The most familiar example is the electron and its antiparticle, the positron. Both have the same mass, but the electron carries a negative charge, while the positron carries a positive charge. Similarly, the proton, residing in the nucleus of an atom, has its antimatter counterpart, the antiproton. The proton, with its positive charge, is mirrored by the antiproton with its negative charge. Again, their masses are identical. Neutrons, the neutral particles within the atomic nucleus, also have antimatter counterparts called antineutrons. While both are electrically neutral, they differ in a property called baryon number, which is conserved in particle interactions. These examples highlight a fundamental principle. Every known particle of matter has a corresponding antiparticle with the opposite charge. This symmetry is a cornerstone of our understanding of the universe. What happens when matter meets its antimatter counterpart? The result is a dramatic event known as annihilation. When a particle and its antiparticle collide, they completely annihilate each other. This isn't a case of destruction, it's a transformation. The annihilation process converts the entire mass of both particles into energy. This energy isn't just released, it's released with incredible efficiency, according to Einstein's famous equation, E = mc2. This equation tells us that mass is just a very concentrated form of energy. The annihilation of matter and antimatter is the most efficient energy-releasing process known in the universe. It's far more efficient than nuclear reactions, even the processes that power the sun. Section 4. The power of antimatter. Energy unleashed. The energy released during matter-antimatter annihilation is staggering. To put it into perspective, consider this. The annihilation of just 1 gram of antimatter with 1 gram of matter would release the energy equivalent of roughly 43 kilotons of TNT. This is more powerful than the atomic bomb that devastated Hiroshima. It highlights the incredible energy density of antimatter, making it a tantalizing, though challenging prospect for future energy production. Imagine a future where spacecraft could travel vast interstellar distances powered by minuscule amounts of antimatter. The concept sounds like science fiction, but the physics is sound. However, harnessing this power presents significant technological hurdles. Producing and storing even tiny amounts of antimatter is a major challenge that continues to occupy scientists today. Section 5. Antimatter in the cosmos, rare but real. If matter and antimatter annihilate so readily, why is there any matter left in the universe? This is one of the most profound mysteries in cosmology, known as the baryon asymmetry problem. The early universe should have produced equal amounts of matter and antimatter. However, we observe a universe dominated by matter. Something must have tipped the balance in favor of matter over antimatter. Despite its rarity, antimatter does exist in the universe. Cosmic rays, high-energy particles from space contain small amounts of antimatter. These antiparticles are thought to be produced in high-energy astrophysical events, such as supernova explosions or near black holes. Furthermore, scientists have observed evidence of antimatter in thunderstorms, demonstrating that these exotic particles can be produced naturally, even within Earth's atmosphere. Section 6. Creating antimatter, a laboratory feat. While antimatter is rare in the universe, we can create it here on Earth, albeit in minuscule quantities. Particle accelerators, such as the Large Hadron Collider, are capable of producing antimatter. These massive machines accelerate particles to nearly the speed of light and smash them together. These collisions create a shower of new particles, including antiparticles. The antiparticles are carefully separated and trapped using magnetic fields. However, producing even a billionth of a gram of antimatter requires enormous amounts of energy and sophisticated equipment. Storing antimatter is another challenge, as it annihilates upon contact with ordinary matter. Despite these hurdles, scientists are making progress in antimatter research. The ability to create and study antimatter in the lab provides invaluable insights into the fundamental nature of the universe. Section 7. Antiatoms and antihydrogen building blocks of antielements. If antiprotons, antineutrons, and positrons exist, can we combine them to create antiatoms, the building blocks of antielements? The answer is yes. In fact, scientists have already created antihydrogen, the simplest antiatom, consisting of an antiproton orbited by a positron. The first antihydrogen atoms were created at CERN in 1995, marking a significant milestone in antimatter research. These antiatoms, however, were short-lived, annihilating quickly with ordinary matter. Subsequent experiments have created larger amounts of antihydrogen and trapped them for longer periods, allowing scientists to study their properties in more detail. The goal is to compare the properties of antihydrogen with those of ordinary hydrogen. The creation and study of antiatoms open up exciting possibilities for testing fundamental symmetries in physics. Any tiny difference in the behavior of matter and antimatter could have profound implications for our understanding of the universe.